Today is inverse trig derivatives part 2, and we're basically going to do the same thing we did for part 2 with our regular trig derivatives, where we're going to take the new derivatives we just learned in part 1, and we're going to go back to some of our common applications. So we're going to look at questions like finding equations of tangent lines, implicit differentiation, finding minimums and maximums, those types of questions. So what I want to do for today is do just 2 examples with you guys so you can see what those look like. And then the assignment I left for you on WebAssign is actually a pretty short one today. There aren't too many questions on it. So let's start with the tangent line question. Again, that's a real common one. Okay. So for this question, our function is x times inverse sine of x. And we're going to find the tangent line when x is 1/2. So we know for a tangent line question, we have to find the first derivative because that's how we find the slope. So let's do that first. And what I notice is this is a product rule question because we have first function is x, second function is inverse sine of x. It's a product. So it's going to be the derivative of the first function, that's an easy one, it's just 1, times the second function, inverse sine of x, plus the derivative of the second function. This is one of the new ones we learned in part 1. The trick is to just know them. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. And then to finish up our product rule, we'll multiply by the first function, which is x. So if we clean this up a little, what we have is inverse sine of x plus, we'll just put that x on top, x over square root of 1 minus x squared. So now for step 2, in order to find the slope, m, we're going to plug our x value in. And x is 1/2 for this question. So we have inverse sine of 1/2 plus 1/2 over the square root of 1 minus 1/2 squared. So inverse sine of 1/2. Now remember, when you're doing inverse trig, it's asking you the question, this is a unit circle question, and it's asking you where on the unit circle does sine equal positive 1/2? That would be pi over 6. Now for the rest of it, we just need to clean up using ordinary math. So inside the square root, let's leave the 1/2 for now. And inside the square root, 1/2 squared is 1/4. So what we end up with, we have the square root of 1 minus 1/4 is 3/4. So we have pi over 6 plus, now what we have is 1/2 over, and it's going to end up being radical 3 over 2. And then those 2's cancel. So what we get for our slope is pi over 6 plus 1 over radical 3. All right, so we still have a little bit of work tomorrow to do. I'm going to clear this. But what I did is up there in red is I typed in the slope we just found. So our slope is pi over 6 plus 1 over radical 3. And to finish out the question, what we need is a point to go with it. We need our point x1, y1. Now we know the x value is 1/2. That was given in the question. To figure out the y value, you go back to not the derivative, but the original question. You plug 1/2 into that. So we have 1/2 inverse sine of 1/2, which would be 1/2 times, we already figured out the inverse sine of 1/2 is pi over 6. And 1/2 times pi over 6 is pi over 12. So that's what's going to go here. So now we have everything we need in order to answer the question. Remember, when you're answering your question, you're doing y minus y1 equals m times x minus x1. And the x1 and the y1 are the point, and the m is the slope. That's written up there in red. So what we're going to end up with for our final answer is y minus pi over 12 equals, and then put that whole slope in parentheses. We need the whole thing. Pi over 6 plus 1 over radical 3 times x minus 1/2. And you definitely just want to leave your answer like that. Don't try to multiply it all out. It would be kind of messy. Okay, so that was an example of a tangent line question when a inverse trig function is involved. I'm going to do one more example with you guys today. This is implicit differentiation. So we're going to find dy dx, and I know it's implicit differentiation because the question that the x's and y's are all mixed up. It's not in y equals form, plus there's more than one y in the question. So when you're doing implicit differentiation, step one is to take the derivative of both sides of the equation, basically take the derivative of everything. So the derivative of inverse cosine of y, now we learned inverse cosine, remember the derivative is the same as inverse sine, except it's negative. So what I'm going to do, I'm going to start with negative 1 over the square root of 1 minus, now remember, since it's a y, I'm not going to do x squared, I'm going to do y squared. And also, since it's a y and we're taking the derivative implicitly, I'm going to have a dy dx on that. Okay, the second one's an easy one. The derivative of e to the x is e to the x. And then on the right-hand side, it's product rule, x times y. So it has to be the derivative of the first is 1, times the second is y, plus the derivative of the second, the derivative of y is dy dx, times the first, which is x. So if we clean this up a little, the first part I'm just going to leave. Negative 1 over square root of 1 minus y squared dy dx plus e to the x equals y plus x dy dx. So when I'm looking at this question, I have a dy dx term here and a dy dx term here. In order to solve for dy dx, I need to group those two together, separate them from everything else, and then I can factor it out. So basically when I do that, let's leave the e to the x on the left. Let's subtract y from both sides to group those together. Let's leave the x dy dx on the right, and then this whole big term here, since it was negative, let's add it to both sides. Okay. Now once you get them grouped, you're always 2 steps away from the answer. Step 1 is to factor it out. And then step 2 is to divide both sides by whatever is left over after you factored it out. So I'm going to divide by x plus 1 over the square root of 1 minus y squared. Which will cancel all of that. And then I'm just going to box it up because it's basically the answer. I ran out of space to recopy or anything. But that is your derivative, your dy dx. It is a little bit messy. There is a complex fraction in there. I'm going to say stop here. It's the answer. It's fine. If you want to try and clean up that complex fraction, you can, but it's not really necessary. So there's a couple examples of what we're going to do today. We're going to be taking those inverse trig derivatives that you guys learned in part 1, and we're going to be applying things like what we did today. Take a look at your WebAssign assignment. Remember, it's not a very long one. It's only 4 or 5 problems today. And try to do those by the end of the week.